Today's class, let us learn Euler's theorem. We know that Euler gave a first published proof of Fermat's theorem. It was during somewhat 1736, but sometimes later in 1760, he succeeded in generalizing the Fermat's theorem from the case of a prime number to a positive integer n, arbitrary positive integer n. I hope you remember what does Fermat's little theorem says. It says if p is a prime, if p is any prime number and p does not divide integer a, then a power p minus 1 is congruent to 1 mod p. Euler gave a first proof for this, but after some times he only gave a proof just by changing this. In fact, it's a tremendous change actually. He changed prime number to an arbitrary integer. Okay, and he wrote his own theorem. It says if n is greater than or equal to 1 and GCD of a comma n equal to 1, then instead of a power p minus 1, he generalized p to an arbitrary integer and he says a power phi of n is congruent to 1 mod n. So let us prove this. Before that, let us look at one lemma which helps in proving this. Okay. Lemma says let n greater than 1 and GCD of a and n is 1 if a1, a2 dash dash a phi of n are positive integers less than n and relatively prime to n, then a1, a2 dash dash a phi of n are congruent modulo n to a1, a2 dash dash a phi of n in some order. Okay, so how it is possible? Let us see. You can observe one thing that this a1, a2 dash dash a phi of n, okay, when you consider this, no two of them are congruent modulo n. Means I say this cannot be congruent to any of this with respect to modulo n. Why? Because see, if some ai is congruent to aj modulo n, then what happens? Before that, let me write. So that no two of the integers a1, a2 dash dash a phi of n are congruent modulo n. Okay, it's because suppose some ai is congruent to aaj mod n in such a way that this I is less than j. Of course, it must be less than or equal to phi of n. Yeah. Then just by the cancellation property, I can just say ai is congruent to aj modulo n. See, since it is mentioned that GCD of a and n is 1, okay, and this ai is less than n and aj is also less than n, and it is given that ai is congruent to aj mod n. What does it mean? It means n divides ai minus aj, which is not possible because see this cannot be possible. It's because GCD of A and N is 1 and AIs and AJs are less than N. AI is less than N, AJ is also less than 1. Since these two are less than N cannot divide AI minus AJ. Therefore, AI cannot be congruent to AJ mod N. That means AAI cannot be congruent to AAJ mod N for any IJ less than phi of N. It lies between 1 and phi of N. Therefore, I can directly write, say, this is same as writing GCD of AI comma N is 1, which is same as GCD of AJ comma N equal to 1. So, because of this condition, this is not possible. Therefore, they cannot be congruent. Okay. So, one thing is over. These numbers are like this is not congruent to any of this. Okay, they are not congruent to each other. Now the thing is, I have to prove these are congruent to these numbers in some order, not necessarily that A1 has to be congruent to A1 mod N or something like that. Okay, so let us see. So I'll take first particular AI I'll consider, say for AI, there exists a unique integer, say b. One more thing we can observe from these two statements, okay? GCD of AI comma N is 1 and GCD of AJ comma 1 is also N is also 1. So from this I can even write GCD of since GCD of A comma N is already 1, it is already mentioned, so I can write GCD of AAI comma N equal to 1. It is because, see, I hope you know this. Suppose GCD of A comma BC is 1, then it implies and implied by GCD of A comma B is 1 and GCD of A comma C is also 1. This GCD of A comma BC is 1 if and only if GCD of AB is 1 and GCD of AC is 1. So from that criteria I can even write GCD of AAI comma N equal to 1. Okay, so now we'll take a particular AI. There exists a unique integer for AI. There exists a unique integer, say b, in such a way that this lies in between 0 and n, for which AAI is congruent to B mod n. Okay, so I'm considering like this: AAI is congruent to B mod n. Since it's mentioned I have already mentioned AAI is not congruent to AAJ mod n. That means this A1, A2 dash dash A phi of n leaves different remainder when I divide it by n. Okay, I'll take that remainder as, say, b. Okay, so that AAI is congruent to B mod n. Now because it's given GCD of AI comma n is 1 and GCD of AAI comma n is equal to 1, I can write GCD of B comma n is also 1, and I know that B is less than n. Therefore, this B belongs to any one of this set A1, A2 dash dash A phi of n. b must be one of the integer among this. Okay, see, it is already given that GCD of a comma n is 1, and we got GCD of ai comma n is 1. Okay, so this ai is congruent to b mod n. Therefore, I can write GCD of b comma n is 1. Since we have considered b, since b is less than n, this b must be one of these integers. Okay. Therefore, that just proves that the numbers a1, a2, a5 of n are identical to this a1, a2, dash dash, a5 of n mod n in some order. Okay, therefore in fact, hence the proof, I can say that is what we have to prove. A1, A2 dash dash are congruent modulo into A1, A2, AR. I just took one such AI. Okay, so this is true for all AIs. Now we'll go for proving Euler's theorem. So from the lemma, I can just write that A1, A2, A5 of n are congruent to, in fact congruent modulo n to A1, A2, A5 of n in some order. Okay, so I can write, say, A1 is congruent to B1 mod n. This B1 belongs to A1, A2 dash dash A phi of n. Some AI is equal to B1. Okay. Similarly, I can write A2 is congruent to B2 mod n. Of course, B2 belongs to this, and also B1 is not equal to B2. Okay, they are not equal. So similarly, I can write A phi of n is congruent to B phi of n mod n, where B1, B2 dash dash B phi of n are the integers A1, A2, A phi of n in some order. Okay, what I do is now we'll take the product of all these phi of n congruences. Okay, what happens is A1 into A2 into A3 like that into A phi of n is congruent to B1 into B2 into B3 dash dash B phi of n mod n. So that is same as writing on taking product of all these congruences, we get A1 into A2 dash dash into A phi of n is congruent to B1, B2 dash dash B phi of n. So always I should write it over here. Okay, mod n. Okay, now this A is multiplied phi of n times, so I can write A to the power phi of n into A1 into A2 dash 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 A phi of n, which is congruent to B1, B2 into B phi of n mod n. We know that these B1, B2, B phi of n are one among this and they are not equal also. So I can just cancel them and I can write A power phi of n is congruent to 1, is congruent to 1 mod n. Since it's mentioned that GCD of AI comma n is equal to 1, I can write GCD of the product A1, A2 dash dash A phi of n comma n is equal to 1. It is because I mentioned no GCD of A comma B C is equal to 1 if and only if GCD of A comma B equal to 1 and GCD of A comma C equal to 1. So same thing I am applying here. Since all AIs are individually relatively prime to n, their product also relatively prime to n. So from the cancellation law we can apply over here. We can cancel this and we can directly write A power phi of n is congruent to 1 mod n. Hence the proof of Euler's theorem. From using this Euler's theorem we can solve many congruency problems. So let us take one such problem. Before going for the problem, I'll mention you something. See, Euler's formula says A power phi of n is congruent to 1 mod n. Okay, he generalized Fermat's little theorem. Okay, so see, if n is prime, if n is prime means n equal to p, and GCD of A and P is equal to 1, then phi of P is what? We know phi of a prime number is P minus 1, right? So I'll just put it over here, then it becomes A power phi of P is congruent to 1 mod n, which is nothing but A power P minus 1 congruent to 1 mod P, which is nothing but the Fermat's little theorem. And these things helps in solving the problems in which say you have to reduce large powers of modulo n. In those cases it is helpful. Suppose you have to calculate A power 37 or say phi value of 100, or you have to calculate say 3 power 256, some particular example like that. If you have then in those cases you can use these two formulas to calculate the values. We'll go for the first problem. Use Euler's theorem to prove A power 37 is congruent to A mod 1729 for any integer A. So we'll do this. We know from Euler's theorem A power phi of n is congruent to 1 mod n, 1 mod n, and now this n value is can I write this in terms of products of prime? That I have to check first, so that I can rewrite these. Okay, so this is, I think if I write 5 into 7, no, it won't be because it is ending with 9. Maybe I'll check. So can write it as 7 into 13 into 19. Okay, so from the Fermat's theorem I can write a power 7 minus 1, a power p minus 1 is congruent to 1 mod n. So, a power 7 minus 1 is congruent to 1 mod 7. A power 13 minus 1 is congruent to 1 mod 13. Similarly, a power 19 minus 1 is congruent to 1 mod 19. Okay. So, this is same as writing a power 6 is congruent to 1 mod 7. A power 12 is congruent to 1 mod 13 and a power 18 is congruent to 1 mod 19. Okay, everything is congruent to 1 modular value of primes. Since A is relatively prime, that means A is relatively prime to 7, 13 and 19. So, when I take powers of A, that will also be congruent modulo 1. There also will be relatively prime, the product. So, I can just write, since A is relatively prime to 7, 13 and 19, powers on the left hand side will be congruent modulo 1. Congruent to 1. That is same as writing a power 6. A power 6 is congruent to 1 mod 7. So, I can write a power 6 into a power 6 is congruent to 1 mod 7. That is nothing but a power 36 is congruent to 1 mod 7. So, a power 36, 12 into 3, so the same is congruent to 1 mod 13. Similarly, a power 36 is congruent to 1 mod 19. So, I'll take up, multiply all together. I'll write, if I multiply everything by A, so that I want a power 37, right? So, we'll multiply each congruent by A. So that I am getting a power 37 is congruent to 1 mod 7, which is congruent to 1 mod 30, sorry, a mod 7, a mod 13 is also congruent to a mod 19. In fact, I can write a power 37 is congruent to a mod 7 into 13 into 19, which is nothing but 1729. So, it's congruent to. So, from the Chinese remainder theorem, this is from the Chinese remainder theorem, we can write a power 37 is congruent to a mod 1729.